interesting topic called scale drawing and similarities. Okay, we're going to start with scale drawing. So, scale drawing is based on a simple premise, and that is, imagine you have bought a plot in Lusaka West. Of course, if you're in Lusaka, you should know Lusaka, but wherever, the plot, it's a 20 by 40, a 20 meters by 40 meters. Okay, then now you go there, you want to draw that plot so that at some point you don't find yourself arguing with someone. So you have got this piece of paper in a book. Okay, how are you going to draw 20 meters and 40 meters? How are you going to draw it? Because 20 meters can't fit here. Meters, it's a longer distance. Okay, think of a plot. How can you draw that plot on a paper? It's going to be very small. Okay, so if you draw something like this, how can you know that which one is 20 and which one is 40? Okay, you need to create a scale. Okay, so that you are able to change this to a small number and this to a small number, so that if again someone has taken the land and you have written maybe 20, 40, and you need to take this back to meters and this back to meters, you can change. Okay, I know most of you can just write 20 meters, 40 meters, but sometimes it becomes critical. You can't just write the letter M to show that it's meters. It has to be precise. It has to be the exact drawing. For those who would maybe pursue architecture or engineering, especially mechanical engineering, this is going to be very cardinal. But in our day-to-day lives, we need it. So that's the science behind scale drawing. So normally scales, we write them in this form. For example, okay, so when we write like this, we mean 1 unit on the map represents 2000 in actuality. Okay, so if this 1 unit is in centimeters, it means even in reality it's 2000 centimeters. So 1 centimeter on the paper represents 2000 centimeters in actuality. Okay, that's what it means. In actuality, it means in reality. Okay, so that's what it means. This side is for the dimension or the measurement on the map. This is the actual measurement or the actual thing. Okay, but the key point is they should all be in the same units. If they are meters, they should be meters. If they are centimeters, they should be centimeters. If they are millimeters, just like that. Okay, so that's the concept. Okay, so this is called the scale of a map. The scale of a map. Okay, so with that understanding, let's say you, as an example, you measure a house and you find that it is 40 meters. Okay, so then maybe someone drew the same house and found that the same measurement that was made, it's 4 centimeters, but they forgot to put the scale. How can you put the scale? Remember, scale is map to actual. Okay, map to actual. So map is 4 centimeters, actual is 40 meters. But remember, they should be in the same units. So you need to change one of these. So you can change meters to centimeters by multiplying by 100. For you to change meters to centimeters, you multiply by 100. So it's going to be 4 centimeters to 40 meters times 100. It's 4,000 centimeters. Then again, the principle is do your best to make sure that they're in the lowest terms. Okay, so you can take this to lowest terms by saying, okay, 4 goes into here, it's 1, and 4 goes into here, it's 1 with the zeros. Don't show the units in the final scale. So the scale of your map, it's 1 to 1000. 1 to 1000. Okay, another example. Let's say a question says, let me just write it. Okay, so the question says a scale of a drawing is n to 50. So the scale is n to 50, right? So they are saying, given that a piece of land on a paper, the scale is n to 50. So given that a piece of land on a paper has a length of 20 centimeters and its actual, it's supposed to be actual length is 200 2000 centimeters. Find n. So we have agreed that on the left we write the map measurement and this side the actual measurement. So n to 50. So we're going to take the 20 centimeters, which is the measurement on the paper or on the map. We write it here. Remember, what is written on the paper is the same as it's more like a map. Okay, so whatever is written, that's what we're referring to as map. Okay, actual measurement, we put it here 2000, and make sure that they are both in the same units. 20 centimeters, 2000 centimeters. That's good. If one was in, let's say the 2000 was in meters, it is supposed to be changed to centimeters. They're supposed to be in the same units when you're about to do the scale comparisons. Okay, from here you can cross multiply. Okay, so 50 times 20 is going to be 1000. Okay, 20,000 times n is going to be 20,000 n. You can divide both sides by 20,000. 20,000. Okay, this goes. So 1000 divided by 20,000, you're going to get 0.5, which is equal to n. It means your n is 0.5. Of course, it's a bad scale. You can't say 0.5 to 50. A scale is always good when you say 1 to something. But anyway, that's the situation here. Okay, that's how to deal with the scale drawing. Now, there are times when we know the scale, okay, but we may need to compare areas. What does that mean? We know the scale, then we need to know the the areas. Maybe I draw so that you understand. So we have this piece of land. Okay, so this, it's maybe 2, let me say 4 to 2, right? Or 4 centimeters, 2 centimeters. Okay, so this is on paper. Okay, then in actuality, let's say it's okay, 40 centimeters, 40 centimeters, and it's not 40, it's 40. 40 centimeters and 20 centimeters. Okay, so yes, it's easy to it's easy to compare the dimensions. By dimensions, I'm referring to the length, maybe the width. Okay, but when it comes to area, the story changes a bit. Okay, if we have been given the area of this, for us to know the area of this, there is something you have to do to the scale. Okay, so if the scale of the length or sides of the piece of land, it's 1 to 2. Okay, that's the scale. So if you want to know the scale you're going to use to find the area, you have to let me see, maybe I give one more example before we start talking about this. I know it's fine. Okay, maybe I just add this. So before we can start talking about areas, the point of the scale I just want to emphasize is to help us know um if we have been given, for example, a measurement on the map, then we can use the scale to predict the measurement on the in actuality. Okay, for example, if they have said, if the length on the map is 40, what is its actual length? You just put 40 on the map, then x on the actual side, then you cross multiply. If they have said the actual width is 10, what is the width on the map? So on the map, you put x on the side of the map. That's the main point here. Okay, now if you want to do the same for areas, it's not that easy. You have to square the scales. What does it mean? You have to do power 2 to the scales. 1 power 2, it's 1. 2 to the power 2, it's 4. So this new scale you get is the scale for areas. The scale for areas. This is the scale for sides. This is the scale for areas. Okay, for you to get the scale for areas from the scale of sides, you have to do power 2. Okay, now that you have the scale for areas, you can compare the areas. So if they say the area of the piece, the area of the land on a piece of paper is 2 meter squared. Find the area find the actual area. Okay, so you don't have to worry, so long as you have gotten the area, the scales of the sides, then you have done power 2, then you have this, you don't have to worry. So you say, okay, they are saying that the area on the map is 2. So mean that the side on the map you put 2, then the side for the actual one you put x, and you cross multiply x times 1, x 2 times 4, 8. Okay, as simple as that. Okay, so now let's picture this situation where they have given us the area. So there's this piece of land on the map. It measures 80 centimeter squared. Then in actual sense, it measures, let me see, 500, no, 50 centimeter. Okay, let me do this. 8 centimeter squared. Then in actual sense, it also, okay, since this is the first example, 4 centimeters squared. And in actual sense, it measures 9 centimeters squared. Okay, so when you have been given this, these are the areas. They are not, by the way, I'm not supposed even to put this. Okay, they have just said the land on the map measures 4 centimeters squared as the area. Then its actual area, it's 9 centimeters squared. Okay, then the first question, find the ratio of the sides, or find the scale of the sides. Okay, it can be ratio of the sides or scale of the sides. So these are the areas, 4 and 9, they are the areas. Okay, they may be the scale of the areas when you compare them, right? Now, to get this, the scales or the ratio of the sides, you have to do the opposite, square root, square root. So it will give you 2 to 3. This is the scale or ratio of the sides you're going to use. Okay, this is the scale or ratio of the sides you're going to use. So if they have said the side on a map is 5 centimeters, what is the actual size side? So you just put 5 centimeters here, x, you do cross multiply. Okay, to give you the visual representation of what's happening. So we have, I'll stop using scale, I'll be using ratios now. We have ratio of sides, right? So if you have ratio of sides, you want to get ratio of areas, you do power 2. Okay, so what you get is the ratio of areas. Okay, now if you have ratios of areas and you want to get back the ratios of sides, you have to do square root. Okay, that's how it goes. You have ratio of sides, you want to get ratio of areas, you do power 2. Okay, you have ratio of areas, you want to get ratio of sides, you do square root. Okay, so that's how to do it. The reason why we need ratios is because they help us to they help us to find the actual side when we've been given the side on the drawing or on the map. They also help us to find the actual I mean the side on the map if we've been given the actual side. Also, they help us to find the area on the map if we've been given the actual area, or vice versa. One more thing before we can say we have understood is there is also ratio of volumes. Let's say there is a drawing of a house. Okay, so if you know the ratio of the sides of the house, okay, you know the ratio of the sides of the house, for you to get the ratio of the volumes of the house. Okay, so ratio of sides. If you want to get ratio of volumes, I'll use V. You have to do power 3. Okay, you have to get the ratio of sides, you do them power 3. That's when you get ratio of volumes. And if you have been given ratios of volumes, you want to get back ratio of sides, you have to do cube root. Okay, that's how it works. So let's say let's look at this example. So the question reads, a piece of land has a side of 1 centimeter on the ground and sorry, it's supposed to be on the map. I made a mistake. It's supposed to be 1 centimeter on the map, and the same side measures 100 meters in actuality. Find A, ratio of sides, B, ratio of volume, C, actual volume if volume on the map is 10 centimeter cubed. Okay, so this is let's see how we can tackle this one. So a piece of land the side of 1 centimeter on the ground, and on the map, and the same side measures 100 meters in actuality. Find ratio of sides. Okay, to find ratio of sides, we know what to do. We just have to compare the given sides, since we have been given the sides. So we have 1 centimeter on the ground and 100 meters in actuality. Okay, so 1 centimeter. So the 1 centimeter on the map, okay, supposed to read it as 1 centimeter on the map and 100 meters on the ground. Let me say that again. 1 centimeter on the map and 100 meters in actuality. Okay. Now we have an issue here, because here we have centimeters, here we have meters. So for us to compare these two, we need to change. Okay, we need to make sure that they're in the same units. So we can change meters to centimeters by multiplying by 100. So 100 times 100, 10,000. So 1 centimeter is equal to 10,000 centimeters. Okay, so our scale is 1 to 10,000. And make sure that there is no number that goes into both, meaning that they are lowest terms, and don't put units. Okay, so this is the ratio of the sides. Okay, now B is saying ratio of volumes. To get ratio of volumes, we just have to do power 3, power 3. So 1 power 3, it's 1. 10,000 power 3, it's 10,000. After write these zeros, 1 2 3 1 2 3 4 1 2 3 4 again 1 2 3 4. Okay, so with a calculator, if you do 10 power 3, you are going to, if you do 10,000 power 3, you are going to get 1 times 10 to the power 12. Okay, let me just see. Yes, 1 times 10 to the power 12. Okay, so this is the ratio of volumes. Okay, so I've answered question B. Question C, actual volume if volume on the map is 10 centimeter cubed. Actual volume if volume on the map is 10 centimeter cubed. Okay, so we have 1 times 10 to the power 12. So they've said the actual volume if volume on the map is 10 centimeter cubed, right? X. So we can do cross multiply. 1 times x, it's x. 1 times 10 to the power 12 times 10, it's 1 times 10 to the power 13 centimeter cubed. Okay, so the units will maintain. Okay, when you are trying to get the actual thing from the map, the units you have been given, they're the ones you're going to get. If you're trying to get the map thing from the actual, the units will maintain. Okay, but sometimes in exam they would say find the volume in meters. Okay, so how can you convert this to meters? That's a story for another day. Okay, but it's good to learn how to change this to meters. Okay, the conversion is simple. 1 meter is equal to 100 centimeters. So want to change centimeter cubed to meters. Okay, but these are not cubed, so to make them cubed you have to do power 3. Okay, so you do power 3 both sides, power 3. So this becomes 1 meter power 3, and this one becomes 1 times 10 to the power 6. Okay, centimeter cubed. Okay, from there you ask yourself, how many centimeters do I have here? Because we want to change this into into meters. So we have 1 times 10 to the power 13 centimeters. So we put them here. 1 times 10 to the power 13 centimeter cubed. This side we put x. We cross multiply and we start dividing. Of course, the question, it was just an impromptu question. I just created it, so it can't come in paper 1 because the numbers are too big and you can't do them without a calculator. Though you can, if you have done standard notations or scientific notations. Okay, so that's all about scale drawing and similarities. I mean about scale drawing. Now there's another concept called similarities. Okay, so similarities is just like scale drawing, but we don't talk about scale drawing. We use the word similarities. So if two shapes are similar, we expect their corresponding size to be the same. Okay, so if we have a jar here, okay, okay, and another jar here, but a bigger or a smaller one this time. Okay, so if we're saying these two are similar, we expect this side and this side, the ratio of these two sides to be the same as the ratio of this size to be the same as the ratio of this size to be the same as the ratio of this size to be the same as the ratio of this size to be the same, just like that. Okay, so it's the same concept. So for example, if they say two jars, maybe there are two jars, a bigger one measure as a height of 20 centimeters and a smaller one as a height of 2 centimeters. So you can say big is this side, to small it is this side. Okay, so if they say find the size or the width of the bigger jar, if the width of a smaller jar is 5 centimeters. Okay, so you just put x here, you do cross multiply, as simple as that. Of course, sometimes they can give you the same thing. The bigger jar is 20, the smaller one is 2. Then they say find the area of the bigger one if the area of the small one is 5 centimeter squared. Okay, so for you to, this is the area. Remember, area, you just don't use this. You need to do power 2, power 2. So that 20 power 2, you get 400, and 2 power 2, you get 4. Then now you can put the area of the small one, then x on the side of the bigger one. Then you cross multiply. Again, they can say the volumes. They can say find the volume of the bigger jar if the volume of the smaller jar is 3. Okay, easy 3 maybe centimeter cubed. So again, for you to get the ratio of the size to ratio of volumes, you have to do power 3. Remember, power 3. So 20 power 3 is going to be 8000. Is it like this? 20 times 20, 400 times 20, 8,000. Okay, I think something like this. Okay, 2 times 2 power 3, it's going to be 8. Okay, then you get the volume given, x, you do cross multiply. I want to show more examples, but I feel like I'm wasting your bundles. Okay, let me just do one more example. Maybe it's going to be very helpful. So the question reads, two similar cups have volumes of 8 meter cubed and 1.5 meter cubed. Find A, ratio of their sides, B, area of the bigger cup if that of a smaller cup is 10 meters. Okay, so what do we do? So they have said we have two cups here. There is one with 8 meter cubed. There is one which has a volume of 8 meter cubed and one with a volume of 1.5 meter cubed. So the one with the volume of 1.5 meter cubed is bigger than the one with the volume of 8 meter cubed. In that, with that kind of understanding, we can say ratio of the sides, we can say big to small. You can even write small to big, it doesn't matter. So in this case, and me, normally, I like starting with small, not big, for reasons that I'm not sure if they make sense, but I always like to start with small. So in this case, small is 8 and big is 125. Okay. If you can reduce them to lowest term, you can, provided you're looking for ratio of the volumes. But anyway, this can also be ratios of volumes because we are comparing volumes. So now they want ratios of the sides. Remember, to find the ratios of volumes from ratios of sides, we do power 3. Now to take back from ratios of volumes, these ones, to ratios of sides, you have to do cube root. Cube root. Okay, cube root of 8 is 2. Cube root of 125 is 5. Okay, so this is the ratio of the sides, 2 to 5. Right. Okay, so now we go to B. which says area of the bigger cup if that of a smaller cup is 10 meters. Now we have a situation here. We have been given they want the area. Okay, we have the ratios of the volumes, we have the ratios of the size, but we don't have the ratios of the area. So we need to get ratios of the areas. Okay, so normally, this is the path. Let me just show you the path. Okay, the thinking, the map. Okay, what goes on when you are dealing with these things. Okay, so here's the understanding. So we have ratio of volumes, right? Then we said to get ratio of the sides, you do what? You cube root. Okay, and we know that from ratio of sides to get ratios of areas, what do? We square. We do power. Okay, we do power 2. Okay, we do power 2 or sides power 2. Okay, here it's volume, cube root of volume. That's how we get here. Okay, then sides we do power 2. Okay, to get ratios of areas. Of course, to go back, we do square root of the ratios of areas. Okay, and even from the sides to go to the volumes, we do sides power 3. Okay, you can't go direct like this. You can, but you need to be skillful. Okay, normally you can't. You have to move from volume to side to area. Okay, or area to side to volume. Okay, that's the mind map that you should be having right now. So now they want the area of the bigger cup if that of a smaller cup is 10 meters. They have given us the area of the smaller cup. They want the area of the bigger cup. What should we do? Remember, let's assume there was no question. We have found the ratio of sides, so it's easy. We just have to do them power 2 to get the ratios of areas. Then using the ratios of areas, we can find the area. But sometimes they wouldn't ask you question 1. They will just give you the ratios of volumes. Then they want you to get the ratios of areas. So in that case, you have to do the whole process. You start from the ratios of volume. You go and find ratios of sides. From ratios of sides, you go and find the ratios of areas. Okay, that's how it can be at times. So we're going to use the longer approach so that you just have a full picture. Otherwise, it's simpler from question A. But what if we don't have question A? That's the question. Okay, so two similar cups have volumes of, so ratios of volumes, we have 8 to 125. Okay, so for us to find the area, we need first ratios of area to use. Okay, so we need first to do cube root so that we get ratios of sides which are 2 and 5. Once we have ratios of sides 2 and 5, for us to get ratios of areas, we have to do power 2. Power 2, we get 4 and 25. Okay, so sorry, I was a bit disturbed. It's supposed to be 25. Okay, so these are the ratios of the areas. Now they have said the area of the smaller cup is 10. So on the side of small, we put 10. On the side of big, we put x. Then we do cross multiply. So 4 times x is going to give us 4x. And 10 times 25 is going to be 250. So it's going to be 4x, 250. Okay, then we'll divide both sides by 4. This goes, so 250 divided by 4, I think it's going to be 2.5. Am I right? No, it's not. 250 divided by 4, it's 175. 175 divided by 2. Am I tired that I can't think? Okay, 250. Okay, let's just do it slowly in the amateur way. 2 here, 2 here. It's going to be 125. 2 here, 1. 2 into 12, 6. 2. Oh, I was right. 62.5. So 62.5. That's the area of the bigger one. Remember, units should maintain. Okay, this is everything about similarities and scale drawing. With more practice, it's easy.